We have, for example, talked about certain situations where we could have, for example, if we have a constant theta operation but increased Mach number, or if we have, for example, constant Mach number operation but change in theta. We have discussed that, and we have discussed, for example, the case where we have a wedge versus cone oblique shocks over a wedge, or an oblique shock wave over a cone. We discussed that. And also we discussed some special cases related to aircraft intakes. There are a few more situations that we need to discuss, but regarding what you're seeing right now, shock interactions and reflections. But before that, actually, we decided with Mustafa Hoca to solve this sample problem to you regarding the application of how we could actually, or one could actually use the information that we have learned regarding oblique shock waves. So we first, before talking about these slides, I will go to the whiteboard and actually go over that example. It's quite simple, but I think it demonstrates quite good how well how we can actually implement the knowledge about oblique shock waves. So let me share the whiteboard first. Then we will come back and continue. And depending on the time today, we will actually finish up the topic related to oblique shock waves, and we will start talking about the other important topic in supersonic flows, which are called expansion waves. So first, let's talk about this problem. Yes, question?
Sorry for interrupting, but I remember it when you said that we solve a sample question. Are we going to have recitation hours, or since our exam is coming?
I have to check with Mustafa Hoca and course assistants. If I remember correctly, there were going to be some recitation hours.
Yeah,
but I may be wrong. Maybe I'm also teaching fluid mechanics this semester. We are having recitation hours in fluid mechanics, but in aerodynamics, I will learn and let you know. If I remember correctly, we were going to have recitation hours, but I have to double check. Maybe I mixed them up.
Okay.
But I will let you know. This sample problem is about this, application of oblique shock waves over a wedge. So basically what we got here is this kind of geometry. So, I mean, the front part of it indeed looks like a wedge, but it's more like a triangle, as you can see, subject to an incoming supersonic flow stream. So some M infinity is involved, which is actually in this problem, it's given as 2. So it's incoming with Mach 2. And of course, basically we have this triangular geometry subject to that kind of, when it's subject to that kind of supersonic incoming Mach number, this will generate some kind of oblique shock wave in front of it with an angle beta. And obviously, as you might imagine, we don't know beta, and that needs to be calculated, but we do know the geometry. So the geometrical angle, this angle is given as 20 degrees. Okay. So as usual, if we designate our flow regions before the shock wave as 1, after the shock wave as 2, and the question says we have this geometry exposed to the free stream Mach number of 2, and the length of the wedge is 30 centimeters. So if I draw these dashed lines, so this is 30 centimeters, so 0.3 meters, this is given for this specific wedge. And the question is, this one is operating at standard sea level condition. standard atmosphere, let's say at sea level, and what the question asks, under this condition, what is the drag coefficient of this wedge? Okay, there's one assumption that is given, that assume the base of the wedge is at P infinite. Assume what we call the base pressure. Generally, this is the term in aerodynamics we use to indicate the pressure at the back surface. So on this surface, this is called the base. So in this problem, it is given that as we have to assume the base pressure is at P infinity, basically. It's equal to the atmospheric pressure. So, and the question is, what is the drag coefficient? So, of course, as you can see, first of all, this is, we have to analyze this problem, and then this problem will be analyzed under using the knowledge that we know. Of course, the thing is, as a general knowledge also, the drag in general, or the drag coefficient, the sources that are, or the physical mechanisms that generate drag on a solid body are can be due to different sources. One of them is basically what we call friction drag. Okay, this friction drag is due to the viscous effects, or we will learn later in the semester what we call due to the boundary layers that are being generated on the solid surface fluid interfaces. Okay, due to these boundary layers, we have some basically friction that is happening between the fluid and the solid that comes back to us, that generates basically what we call a friction drag, or what we can call also viscous drag. Viscous drag. Okay. Now this is one contributor, I can say, to the total drag itself. Another contributor is what we call pressure drag. So this pressure drag is due to, or let me put it this way, only due to the pressure distribution happening or being generated on the body due to the fluid flow around it. So due to this fluid flow, there will be some pressure distribution on this surface. The pressure distribution on the base is already given. There will be some pressure distribution on this surface, and that if that pressure distributions are not balanced along x direction, so this is our x coordinate, x direction is our the main direction that we're interested in terms of drag, because drag is defined as parallel to the free stream velocity vector. In this case, it's along x direction. So basically, if there is a pressure imbalance, that will generate a drag force along x direction. So there is this thing called pressure drag. There are other types of drag as well. If you remember from aerodynamics 1 class, we have, for finite wings, we have induced drag, for example. If you can refresh your memories regarding aerodynamics 1, for finite wings, due to the tip flow leakage from the pressure side to the suction side of the wing, therefore a span-wise flow is generated, which basically in turn generates a tip vortex. That tip vortex effectively induces a vertical velocity component on the flow that is oncoming towards the wing. So that changes the angle of effect, the angle of attack of the flow oncoming towards the wing. So that generates eventually an induced drag. So this was for basically, this is true for both for subsonic or supersonic flows, but for when we are dealing with three-dimensional finite wings, basically. Now, when this question asks you about what is the drag coefficient, what the question really asking is what is the pressure drag? So this is the question is what it is really asking, because of the fact that right now we did not learn how to calculate this right now. We don't know. We will learn it in the coming weeks. And we are dealing with mostly a two-dimensional shape, so we are not really concerned with induced drag, at least in the context of this problem. So the question is mainly asking, when it says what is the drag coefficient, it's mainly asking what is the pressure drag that is being generated on this body. So basically, as then you might guess, we need to analyze this problem using what we have learned so far. So we are dealing with inviscid compressible flow theory. So our assumptions are, first of all, we will assume inviscid flow and steady flow, inviscid steady flow. And second assumption is already given, P base is given as P infinity, that is given. And we will assume calorically perfect gas, so we can use certain equations. And we will assume we are dealing with adiabatic flow, so there is no heat transfer to or from the solid body that we are dealing with. So basically under this and under in the supersonic flow condition, knowing that oblique shock waves will be generated, obviously what we need to know is, since we are interested in the pressure drag calculation, we need to calculate the pressure distributions on the surfaces. So I need to calculate the pressure distribution here on the surface, let's say here on this surface and also on this surface, and then I will use them to calculate the drag acting on this body. And how do we know, how are we going, and these are, by the way, static pressures, okay? Static pressure is the pressure that causes the actual loading on any flying object. So I need to know static pressure on the surface, which I can safely assume that it is going, and I'm ignoring the boundary layer effects, and we will see later in the topic of boundary layers, even if there is a boundary layer, the static pressure on the surface is pretty much the same as the static pressure in this free stream above the surface. So we will see that later actually when we do what we call an order of magnitude analysis in the boundary layer theory. In the coming weeks, we will show that. But in any case, in this problem, we can say that P2 after the shock wave, whatever static pressure we have after the shock wave, is basically being, or it's the main pressure that is generating the pressure force acting on these two surfaces. So I just need to the first step is to calculate, find out what is P2 after the shock wave. And then since we have some geometrical information, like we have a 20 degrees angle and a 30 centimeter chord, I can say that is 0.3 meters is given. So I do have some geometrical information. I can use that to combine with the pressure information to actually calculate the axial force acting on the object, which is the drag. So therefore, that is what the problem is in fact asking from us. So therefore, I need to apply my oblique shock wave knowledge. So of course, the first thing we need to find is what is beta. I need to know the shock angle so that I can actually calculate the static pressure ratio, because we know, at least we know the equation from our class notes. The static pressure ratio in this case is, or it can be calculated using this equation, gamma plus 1, and then the normal component of the Mach number before the shock wave minus 1. And the normal component of the Mach number before the shock wave is simply the incoming Mach number or free stream Mach number times sine beta. So I do need to know the shock wave angle to be able to calculate the static pressures. And how do we calculate this? From basically using theta beta m diagram. So using theta beta m diagram. So theta is 20 degrees here. Mach number is Mach 2. So we need to calculate beta using the procedure that we have learned last week regarding theta beta m chart. If you can revise or you can rewatch that video if you don't know how to do that. Then using theta beta m diagram, you can find that beta turns out to be equal to 53.3 degrees. Just a quick reminder, in that chart, these were our axes. Only thing we need to know, and there were distributions like that for different Mach numbers. So we need to find the line for Mach 2. Mach 1 is equal to 2. And so on that line, our theta is given as 20 degrees. And then we take a straight line out at 20 degrees and then get the weak shock solution. So it's 53.3 degrees is going to be our beta shock wave angle at Mach 2 and at theta 20 degrees. In this case,
Hocam ben bir şey merak ediyorum da
evet.
static pressure'ı biz şeydeki surface'deki static pressure nasıl calculate ettik, bir daha anlatabilir misiniz? Galiba kaçırdım ben orayı.
Static pressure, surface'deki static pressure, surface'in üzerindeki akıştaki static pressure'la aynı diye düşünüyoruz.
Anladım. Peki, teşekkür ederim hocam.
Tamam. Çünkü arada değiştirebilecek hiçbir şey yok. Bunu değiştirme ihtimali olan, buraya Türkçe anlatayım. Sonra İngilizce yaparım. Burayı değiştirme ihtimali olan tek şey burada bir boundary layer olması, ama boundary, onu da anlattım biraz önce. Boundary layer olsa bile bu static pressure değişmiyor. Surface'te hissettiğin static pressure bu strip, buradaki akıştaki static pressure'la aynı çıkıyor. So therefore, if you can find P2, we will apply it as the static pressure that is being applied on these surfaces here. That's why we are trying to find P2 basically. And in order to find P2, therefore I need to know beta using this chart. And now beta is 53.3 degrees. And from M1 is given as M1 is equal to 2. So sine 53.3 degrees times 2 gives my normal Mach number component, which becomes equal to 1.6. Okay. And now substituting this into the pressure equation, P2 over P1. So I get the ratio for P2 over P1. And this becomes equal to 2.82 for a calorically perfect gas, and I assumed gamma is equal to 1.4. So we have 2.82 times higher pressure after the shock wave, and P1 is the pressure, static pressure before the shock wave. And the static pressure before the shock wave is basically equal to P infinity. Numerically, the value is equal to atmospheric pressure at sea level, because that is also given. But I will just keep it as P1, because eventually it will cancel out during the drag calculation, as we will see in a second. So now I do have an information regarding P2. And just to demonstrate, I will draw another sketch here of this triangular flying object. Okay, so basically on this surface, we do have a pressure distribution or forces, let's say, due to the pressure distribution. Now you know that forces are acting always normal to the surface and pushing towards the surface. This is how we define pressure forces. and we have 2.82 times P1 acting on the surface. Similarly, we have a pressure distribution on the bottom surface as well. So I guess you know where I'm going with this. We have to find out the total force component along x direction. So this is also 2.82 times P1. And this is 20 degrees, and this is 30 centimeters, so 0.3 meter, what we can say chord. On the base, we have a pressure distribution, or we have a force distribution due to the pressure on the surface. Maybe I should here say, to be more correct, pressure, this much pressure times the area actually. So that makes it a force times area of this surface. And here I have P1, which is equal to P infinity. So it times area of the back surface or the base. So that basically I have to figure this out. And to calculate the drag force, and drag force in this case is the force along x direction. So anyway, so 20 degrees is given, and let's call this chord. And what else? If we do a little geometry here, so half of this triangle, this is chord, this is 20 degrees, and this is, let's say, this is L long. So basically, sine 20 degrees is simply, I'm sorry, not sine, of course, cosine 20 degrees is simply C over L. And therefore, the length of one of the sides is C over cosine 20 degrees. Okay, so that's the length. So therefore, if we now calculate the drag force, and again, let's keep our coordinate system here, x positive to the right, y positive towards up. And if I do the drag calculation, let's say, first of all, we have the forces due to the side surfaces, which are L long. So I need to take that into account. And we have a symmetrical situation, meaning we have zero angle of attack, meaning our free stream Mach number or free stream velocity vector is at 0 degrees compared to our chord. So zero angle of attack. So we do have a symmetrical basically pressure distribution. So in terms of y, in terms of force balance along y direction, everything cancels out. But in terms of force balance along x, I need to take both surfaces into account. So I have to start multiplying with 2 times the pressure, 2.82 times pressure 1. And then the area, so which is basically L C over cosine 20 degrees is the L, and I need to multiply this force by sine theta again, so sine 20 degrees. So this will give me the force component along x for generated due to both of the side surfaces. However, of course, I need to multiply also with the depth, but I'm assuming right now the depth is 1. So I will put a note in a second, but this is the force acting due to acting on the two side surfaces that are situated at 20 degrees from the horizontal. So minus, I need to include the pressure due to the back surface. If my notes are correct, this must be equal to 2 times P1, which is the base pressure here, times chord times tangent theta, if this is correct. So if I reorganize this and let's put a note here, this drag is per unit width, let's say per, or to be more correct, let's say per unit span. So everything is written in terms of P1, and therefore I can reorganize this here quickly. So 2 times P1 times chord times tangent theta, 2.82, and we do have a tangent theta here, as you can see, 2.82 minus 1. So this becomes equal to 2 times P1 chord tangent theta times 1.82. 82, why is it 81 in my notes? But so this is the drag force, but we are asked, the question asks for drag coefficient, so CD, and CD, in order to obtain CD, we need to non-dimensionalize it with free stream dynamic pressure and chord. And free stream dynamic pressure, if you remember again from our aerodynamics 1 class, this is equal to Q infinity is basically rho infinity V infinity squared. So, but instead of this, I can write 1/2, and let me keep the subscript 1 here, because before the shock wave and free stream conditions are basically identical. So if this is going to be equal to 1/2 rho 1, now instead of V1 square, I want to see Mach number there. So basically what I do is I multiply it with gamma times P1 and divide by that as well. So this becomes this becomes equal to gamma P1 over 2 A1 square, basically V1 square, and because gamma P over rho is equal to, if you remember, the speed of sound, so this becomes equal to gamma over 2 P1 and 1 square. This is the this is the dynamic pressure equation written in terms of P1 and the free stream Mach number. So I want to use that here. So the drag is equal to basically 2 P1 chord tangent theta 1.82, and then divided by now Q infinity. So gamma over 2 P1 and 1 square times chord. So do the necessary simplifications, and then what do I get? I get that this is equal to 4 times tangent theta times 1.82 divided by gamma and 1 squared. Okay, let me check that if this is correct. It looks like it's correct. And then if I just plug in the numbers, m1 is equal to 2, so m1 squared is 4, gamma is equal to 1.4, theta is 20 degrees. So I plug in all the numbers, the drag coefficient turns out to be equal to 0.47. Okay, so assuming that this is an inviscid flow application, so we ignored the presence of boundary layers and viscous effects. So, by using the given information, like base 1 pressure is given, for example, we were able to calculate for a triangular shape like that, the total drag acting on it. Well, I say total drag because in the context of this specific problem, it is the total drag because we ignored this and we ignored this. So it is the total drag in this case. But So it becomes equal to, I mean, we got the drag value itself in terms of newtons, which is this here, this is newtons. And the drag coefficient becomes equal to 0.47. If you can imagine, for example, a slight variation to this problem, you would do exactly, I mean, you would follow exact same methodology, but you will end up with a different result. For example, let's say you had M1 equal to 2, but coming in at an angle. Let's say it was coming in at an angle of attack. M1 equal to 2 again, but coming in, let's say, at 10 degrees. Okay, that would generate a different drag coefficient, and in fact that would generate a lift as well. And the reason, I guess you could imagine, because the thing is, if this is the case, you would lose the symmetry on the pressure distribution. You would not have a symmetrical pressure distribution on the top surface compared to the bottom surface. Why would we have an asymmetrical pressure distribution? Because as soon as we have an angle of attack, right, the deviation angle that the flow sees, for example, at the top surface, would not be 20 degrees anymore. The geometrical angle is 20 degrees, yes, it is fine. But if it's coming at 10 degrees, the flow will not be turned 20 degrees when it hits the solid surface, okay? Just to demonstrate that, maybe let's talk about another example. Let's say M1 is incoming at 20 degrees. Let's say this is 20 degrees. So tell me what kind of shock pattern would we have on this triangle if it's coming in at 20 degrees. And theta angle is also 20 degrees here, the same geometry. But now our angle of attack is 20 degrees. What kind of shock pattern would we have on the top and bottom surfaces? Somebody tell me. Any volunteer?
Hocam, could you ask the question again?
We have the same geometry, right? Triangle, 20 degrees half angle, wedge. The free stream Mach number is not coming at 0 degrees, but it's coming at 20 degrees. What would happen then?
Hocam, can I answer?
Of course.
I think the bottom sides act like a ramp to the flow, so we will observe an oblique shock wave at the bottom sides, but flow is tangent to the upper side, so there is no shock wave or normal shock wave maybe.
You are exactly right. This is correct answer, but I will ask one more question in a second. You are right. The flow is parallel to the top surface. At least in the context of this problem and what we learned so far, there will not be any shock wave at the top surface. It's just going to be parallel, because the shock wave occurs because there is a need for the flow to change direction. If it's coming at 0 degrees, it needs to change direction and follow like that, right? Normally. So that need to change direction is achieved by this shock wave. If there's no need to change direction, there will not be a shock wave here. But there will be a shock wave, as you said, on the bottom surface. You are right. But then, do you think the shock wave angle will be the same as our original case, which was 53.3 degrees, or would you think that it's going to be different?
It should be higher.
It should be
Isn't
higher,
it
right?
detached shock wave actually?
Hmm?
Isn't it a detached shock wave actually?
I don't know yet. But first of all, I know that it's not going to be 53.3 degrees anymore. Okay. And in order to answer your question, whether it is going to be detached shock wave or whether it's going to be an attached shock wave, I need to know, I mean, the main thing that I need to know is how much does this original vector have to turn to be parallel to the surface? In the original problem, it had to turn 20 degrees, right? Now, how much does it need to turn? If it's
40.
yes, right? If it's coming at 20 degrees, now it has to turn 40 degrees. So although my geometrical angle is, theta angle is given 20 degrees, if the flow is incoming at an angle, it needs to turn 20 plus another 20 so that it will be parallel to the surface. So our theta angle that needs to go into the oblique shock relations or to the theta beta m chart must be 40 degrees, not 20 degrees. Well, if the incoming Mach number is 2 and the angle is 40 degrees, will it be still attached or detached? I really don't know right now. I have to check the theta beta m chart. Maybe it will be detached, okay? Maybe that turning maybe is too high. So as you see what I'm getting at here, the important thing or the message that you should get here when you are trying to understand how much, trying to understand what kind of beta that we are going to find and everything in a problem like this, you have to check how and even if the geometrical angles are given to you, what you in reality have to check is how much turning will the original vector will have to experience to be parallel to the relevant surfaces, to the top surface here on this side, to the bottom surface here on this side, right? That is the thing, that is the actual theta value that you should be concerned about when you need to deal with theta beta m relation. Did you understand this, everyone?
Hocam ben pek anlayamadım ya.
Sen pek anlayamadın ya. O zaman
Ya benim anlayamadığım kısmı istiyorsanız daha detaylı söyleyeyim size.
söyle bakalım.
Benim kafamı karıştıran kısım şu. Şimdi bu 20 degree'lik angle'ın paralel olması gereken şey bizim surface'ımız mı?
Evet.
Yoksa ben daha önceki derslerden oblik şoka paralel olduğu zaman şey olmadığını hatırlıyorum. Hani tangential'sa oblik şoka o
Oblik
zaman
şok,
şey olmayacaktı. Herhangi bir değişim olmayacaktı yanlış hatırlamıyorsam. O yüzden surface değil de oblik şok olması gerekmiyor muydu?
Oblique shock bu şu anda it's the least of our concerns. I know nothing about oblique shocks. Okay, let me draw this here. What I only know is this. I have a triangular geometry with 20 degree angle, yes? And I have an incoming flow Mach 1 at 20 degree angle. I have no idea about oblique shock waves. I have no idea about what kind of shock pattern that is going to form on it. Only thing that I know is that when the flow is incoming like that, it will not have to go through a direction change compared to the top surface, yes? So I'm not expecting to see a shock wave there, because a shock wave can only occur if there is a need to change the free stream velocity vector direction. Did you understand this point?
Yes.
Good. That is the story of the upper surface. On the bottom surface, the flow, when it's flowing near the surface, it needs to be parallel to the surface, right? So on this surface here, like that, on the bottom surface, like that. So the thing is, when going from this vector to this vector, obviously the flow needs to change direction, yes? And in a supersonic flow, that direction change can only be imposed through a shock wave. So there must be a shock wave here on the bottom surface. On the top surface, no. Well, in reality, if you really think about real world problems, there will probably be a more complicated flow here, but in this simple analysis of inviscid steady flow, there will not be a shock wave here, because there is no vector direction change. Here, there is indeed a vector direction change, and this vector changes direction to 40 degrees below horizontal. So this 40 degrees goes into my calculations to calculate the beta angle of this shock wave, okay, from theta beta m diagram. And up here, there is no shock wave.
Anladım şimdi. Teşekkürler.
Okay, guys, this is important point. So because normally, you know, when we teach about stuff like this, you always get used to seeing sketches like our very first sketch where M1 is incoming parallel. So what we are not telling you, or also in the books, they are not telling you, there's a secret information here. You have to dig it up yourselves. That information is the angle of attack. Nobody tells you about the angle of attack. Here it's 0. So this kind of prevents the students about thinking more about this subject, which is, I think, of very importance, very important. If it's 0 degrees, you automatically assume that, okay, this is my beta angle, and then I will use that. But as soon as you are faced with this problem, you need to be careful. That's what I'm all trying to say. Okay. And if it's, so I try to discuss one extreme case, like when it's equal to 20 degrees, which causes this pattern. But of course, when it's equal to, let's say, 5 degrees, then now you need to be concerned again about how much direction change would this vector go through when incoming with 5 degrees. It still has to be parallel to the surface. So from 5 degrees, and here it's 20 degrees, it needs to go through some vector direction change. So there must be a shock wave here as well if it's incoming with 5 degrees. If it's incoming with 5 degrees and this is 20 degrees, there will be also another shock wave here, right? So this angle of attack basically has a big impact on your shock wave pattern, and therefore the pressures after the shock wave, which could be different if it's asymmetrical. If it's not symmetrical, P2 upper and P2 lower could be different, generating drag, in addition generating lift as well. Did you understand this point? I hope it's a little bit clear now, but just you know, giving you some this alpha related information because it's not generally in the books. Okay, is this point clear? Yes or no?
Yes, hocam.
Peki. Okay, then I will give you 10 minutes to think about it. It's 2:30 already. Then we will continue with our class material. So, okay, great. Let's give a break here. I will meet you at 2:40. Okay, can everyone see the slide on my screen?
Yes, hocam.
Good. Okay, so now there are two topics left actually regarding oblique shock waves. Now, the first one is regarding shock reflections, interactions and reflections. Now, here, basically what you're seeing is a flow, a supersonic stream inside a closed duct, basically, because this could be like inside, this could be inside the intake of your aircraft, of your supersonic flying aircraft, engine intake, for example. So here we do have M1 that is greater than 1. As you see here, we have a ramp. So at sitting at theta angle, M1 is incoming parallel to the surface. And of course, that creates an oblique shock wave, which sits at a beta 1 angle. Now, this shock wave, since we do have another wall at the top, so the question that we're trying to answer here is what happens if there are more than one solid surface, and this second solid surface at the top is the top wall basically. So this the first shock wave will come and hit the top wall, and the angle will be the same as beta 1. So now the thing is, after it hits this top wall, it's going to get reflected. Okay, it's a wave, so it will get reflected, and then there will be another oblique shock wave sitting here at an angle, which we call the reflected shock wave. Now, the shock wave angle is not going to be equal to beta 1 anymore. It's a different angle. It's called capital phi here, Greek letter phi. So the question is, how much is this phi? Okay, and because at the end, for example, if you would like to calculate the flow properties at station 3 after the second shock or after the reflected shock, how can we actually find it? So of course we need to start from the beginning. So the first one is we have a given M1 condition. Given M1, it will be some supersonic Mach number, and given theta, which is our first ramp, I could calculate beta 1. So I can easily from theta beta M chart find out beta 1. And then I can therefore calculate all flow variables, the pressure jump, temperature jump, density jump across this first oblique shock wave, which is written as incident shock here, the first one. So I can basically calculate everything at station or region 2 after the first shock wave. Now the thing is, the direction of the second, or the direction of the velocity vector or the Mach number vector after the first shock will be parallel to the surface. So will be parallel to the surface which is inclined at theta angle. So this vector will be moving at theta angle with respect to the horizontal, right? So with respect to the x-axis in this case. So, and it will be going down, but the thing is, it will have to pass through this reflected shock wave, and the effect of this reflected shock wave has to be such that it, after this reflected shock wave, it will be in region 3, and in region 3 it will have to obey the rule that it has to be parallel to the to the geometrical surface which enforces the flow direction. So it has to be parallel to the surface here. So since the wall is aligned with the x-axis here, the vector, Mach number vector, has to be parallel. So which means that it is incoming at an angle theta before here, and it has to, this vector has to return 20 degrees, it's not 20 degrees, it was 20 degrees in our example, so I'm confused now, but it has to turn theta degrees, sorry. It has to turn theta degrees down now. So this shock wave angle, this second reflected shock wave angle has to be based on that. So the difference is that in the first case when it's trying to jump from region 1 to region 2, it was incoming with M1 and getting turned 20 degrees. And here it again has to turn 20 degrees, but now my free stream Mach number is different. Mach number M2 is not equal to M1. And in fact, I do know that, and it can be calculated from shock wave relations, that M2 will be less than M1. So we are talking about still a supersonic incoming Mach number as M2, but it will be a smaller supersonic Mach number compared to M1. So we are talking about now a shock wave that generates flow turning, right? That generates flow turning at 20 degrees, but incoming Mach number is basically smaller. So as is written here, So because of this reason, because of the fact that M2 is less than M1, the reflected shock wave is actually going to be weaker than the incident shock wave, or weaker than the first shock wave. Weaker meaning that, first of all, the phi angle will be smaller than beta 1. And also, first of all, it's not going to be equal to beta 1 because of this reason. Plus, it's going to be weaker, which means that the pressure jump, the temperature jump, or the pressure ratios, the temperature ratios, the density ratios will be smaller than the ones that we had when we were jumping from 1 to 2. So when we are doing this jump from 2 to 3, it will be a weaker shock wave. It is the same theta as it's written here, but at a different now incoming Mach number M2, which is smaller than M1. So the reflected shock wave will be a weaker shock wave. And so therefore, using this M2 and this theta, now we can calculate, again using the theta beta M chart, the shock wave angle, the reflected shock wave angle now for this case. Okay. Now, there is one problem before I go to the next slide. And that problem is this. Now, my Mach number is different. So M2 is different than M1, and it's actually smaller than M1. So it's a different Mach number. But I still have to learn, I have to turn 20 degrees. The problem is, in the theta beta M chart, this means that, first of all, if I can try to remind you again, the chart here, beta versus theta, and we have these constant Mach number curves, right? So let's say in the first case, theta was somewhere here, right? Somewhere here, and then I got the beta 1 angle from here, and then my Mach number dropped to M2 level, let's say, and in the theta beta M chart, as I go this way, Mach numbers get reduced. So let's say the second line is M2, the first line is M1, and I'm now when I'm at region 2, after the first shock wave, I'm operating at M2 on M2 line. So I'm operating on M2 line. The problem is when the flow needs to turn theta degrees back to the horizontal, and theta degree is the same as the ramp angle here, it could be out of the solution domain of this Mach number. So this theta degrees could be out of the range of this smaller Mach number, which means that then what's going to happen? Because then, first of all, I cannot have a reflected shock wave because it's not giving me a solution. In that special case, basically what happens is a little more complicated flow pattern occurs. And when, as is written here, this occurs when M2 is lower than the minimum Mach number for the given theta. So if it's just too low, then the oblique shock that is generated in the first case, this one, cannot reach the upper wall through a straight line. So it cannot just go like that. Because since in the first case, basically this one, when M2 is too low with the given theta, this cannot generate an attached shock wave. Basically this generates a detached shock wave for this reflected shock. So it's like having a normal shock at the wall. So this kind of normal shock merges with this oblique shock wave here in a complex pattern, and then goes like that again, kind of generating a shock wave pattern as you are seeing here. So this one basically turns into more or less a normal shock wave here attached to the wall, crossing the wall here. And then the reflected shock also gets a complex curved shock wave pattern like that. So when we are designing intakes, we have to take this one into account as well. When, especially for those types of intakes where we end up with shock waves inside the intake inlet duct. Sometimes we design inlets such that we don't have actually any shock waves inside the inlet, but for some aircraft, depending on the aircraft design and aircraft flight Mach, this aircraft geometry and aircraft flight Mach number, design Mach number, we could end up with generating shock waves inside the inlet. So we need to be careful about this condition, because if we end up having this would, since it's almost acting like a normal shock wave here, the pressure loss across this jump will be huge. So we don't want that. Of course, this complex shock wave pattern will also, let's say, will also interact with the boundary layers on the surface and everything. So there could be more severe or more, let's say, complicated flow patterns, which even reduces the efficiency of the inlet that we are dealing with. So this is one issue that we need to be careful about when we are designing aircraft intakes or any duct, any closed duct flow that carries some supersonic flow stream, for that matter. And this another example of interacting shock waves is when we have two ramps. So we have one ramp on the bottom surface sitting at θ1 here, and one ramp on the top surface θ2 here, and it's again like a closed duct flow problem. It's an internal aerodynamics problem, not external. So we have a supersonic flow stream, and then we have these ramps. So we have one oblique shock wave generated at the bottom corner. So this, and by the way, assuming θ1 and θ2 are different, and using theta beta m chart, you can actually calculate the shock wave angles here and here on the bottom surface and the top surface from both sides of the channel, as it's written here, the left and right running shock waves. So it's talking about these two shock waves here. Now, the thing is, when we have that, they will cross each other. They will cross each other. And this is a little bit more, even more complicated situation. And so what happens is, since we have two ramps, this vector must be parallel to this wall, this vector must be parallel to this wall, and after their cross-section, there must be some shock waves, two additional oblique shock waves, such that if, of course, if there are no additional walls downstream, not to complicate things even worse, so we ignore them. So at this stage, so then basically these two vectors must be generally parallel to each other. So this means that in order to find this shock wave angle, you need to know how much this vector has to turn from this angle to this angle, and how much this vector has to turn from this angle to this angle. So that will give you the shock wave angles, let's say, with respect to the horizontal for this shock wave and for this shock wave. And when these two flow streams meet with each other, generally what a boundary is created, which we call a slip line. This dashed line is that slip line, and the physical condition is that across the slip line, the static pressures must be equal, generally P4. So this is 4, this is 4 prime. P4 must be equal to P4 prime, so there wouldn't be any sudden pressure jump. And V4 must be parallel to V4 prime. There wouldn't be any basically cross flow. And there could be differences in, for example, temperature in between these two streams and densities. and also, as it's written here, most noticeably entropy levels of S4 and S4 prime, and therefore stagnation pressures may not be the same. Most important conditions are the fact that static pressures will be the same and velocities will be parallel. Velocity direction will be parallel. It is a quite important issue, and in fact, some of our students, some of our masters and PhD students, and some of our previous graduates working. I know my students there and our older students working at TÜBİTAK SAGE or Roketsan are dealing with these kinds of problems when they are designing, for example, intakes for supersonic missiles. Okay, so once you graduate, if you end up working in one of those institutions, you may end up with working with similar problems like this. And if you end up working at TUSAŞ and some supersonic project, you could also end up with similar problems, working on similar problems like this. So these are quite important. Theoretically, they can be calculated with the things that we have learned so far, but generally, in a real life application, we do perform first-hand calculations based on theory, but we also do lots of computational fluid dynamics analysis, and also lots of, if we can, experiments in supersonic wind tunnels to actually see the shock wave interactions and reflections and their geometrical layout, at least, to see, optically observe while just taking pictures, the beta angles, the actual beta angles that are generated in the real geometry, for example, in a supersonic wind tunnel test. And to check if they are actually consistent with our theoretical predictions. So another example is basically interaction of what we call two left running shock waves, meaning that we have now two ramps again, but on the same wall. So we have the first ramp that sits at a theta angle, theta1 here, followed by a second ramp sitting at a theta2 angle here. This is also very common usage in aircraft supersonic inlet design. We have generally, I think I talked about it also before, we generally have we can have potentially two or more ramps sitting at different angles. So we generate different oblique shock waves. So the first shock wave is here. From the first ramp, the beta1 can be calculated knowing M1 and theta1. And then M2 will be parallel to this wall. M2 is parallel to this wall. It will be smaller than M1, but supersonic. And then it will have to rotate from this angle now to this angle, okay? And then you see it will not rotate with its theta. All the geometrical theta is this one. Its actual rotation will be less than theta2, as you can see. So the second oblique shock wave angle will have to be calculated according to that. But the problem is when these two shock waves meet, and they also intersect with each other, as similar to the case in the other problem in the previous slide, they will intersect with each other. And basically they will merge with each other, a third shock, continuing with a third shock wave, this CD line here. So the incoming supersonic flow stream, the fluid particles basically that are incoming at this level will have to go through these two shock waves, but the fluid particle incoming at this level will have to go through this shock wave. So the shock wave from C to D. So this means that, again, this creates what we call, I guess, slip line, and generally when this happens, a reflected wave is also created when they intersect. But the general condition is similar along the slip line, similar to what we have seen in the internal flow problem case in the previous slide. So here our static pressure across the slip line must be the same, and the velocities at 4 and 5 must be parallel to each other. Okay, so this could also happen when we have this kind of interaction of two shock waves that are generated by two ramps. And our final case, I think this is the final special case, which we previously talked about already, but let's talk about it again, is the case that when we do not have a solution for using our theta beta m relation or theta beta m diagram, when theta is larger than theta max for a given Mach number, as we have discussed before, we do not see an attached oblique shock wave. The shock wave gets detached, and even if it's a pointed sharp geometry with a sharp corner, we can still end up having a detached shock wave. And in reality, if it's a blunt, if the body has a blunt leading edge like this in the sketch here, we also generate a detached shock wave. Now the thing is, now we discuss a little bit more details about detached shock waves here. As I said, this can happen in near aircraft intakes. It all depends on whether our theta selection of the ramp, theta selection is whether it's larger than theta max or not, or whether we have a blunt leading edge or not. If those are the cases, we have this detached shock wave as given here. And now, for example, we investigate this zone by zone. For example, let's say we have a streamline incoming at A, at this level, okay? At this level, the flow will basically go through a very strong normal shock wave. Incoming flow is supersonic, and I mean, maybe I should say not very strong, but I should say relatively stronger shock wave, and it is going to be very close to a normal shock wave. So practically, when you are a streamline, when your fluid particle moving along the streamline A, you would go through a normal shock wave, and just after this shock crossing here, you will end up at subsonic conditions after if you are moving along A. So this region will be basically subsonic. Now, as we are dealing with a detached shock wave, which is curved, as we move along to upper locations, so let's say now we are discussing a fluid particle that is moving along B. Now, it is not going to be the shock wave is not going to be as strong as the one that we have at point A. It is going to be a little bit inclined, but still a quite strong shock wave. So most probably there will be still a subsonic flow after that. So as the curved detached shock wave, or sometimes we call it bow shock, by the way, bow shock. As this one gets turned more towards back, so it becomes more eventually when we go to B to C to D to E, it eventually becomes weaker and weaker and weaker and weaker. And therefore, since it's getting weaker, at some point, the incoming supersonic stream will not go to subsonic anymore. So after the shock wave, it will be still supersonic, but maybe a little bit less value than the incoming Mach number M1. So basically, there will be a boundary between the subsonic and supersonic regions, which is indicated by this dashed line here. And on this dashed line, and before this dashed line, by the way, when streamlines coming here, you know, any streamline coming here will have to follow the blade surface like that. So they will have to be initially initial subsonic, supersonic, then suddenly subsonic, and then they will accelerate, go through this dashed line, which we call the sonic line. They will go through Mach equal to 1 line, and they will accelerate to Mach numbers that are greater than 1. They will accelerate to supersonic conditions. So for, let's say, symmetrical conditions like that, and one coming axially, we will end up with two symmetrically oriented sonic lines just in front of the nose of the body, or just behind behind the detached bow shock wave. So and after that the flow becomes sonic. If you go, supersonic after the sonic point. If you go very far away from the body, like here point E symbolizes you are so far away from the body, the flow does not even feel the presence of the body. Okay, I mean, in the sketch you see it's not that far, but you know, you can put dots here. So let's say it's very far. At very far away, the shock wave will become so weak that it will just turn into what we call a Mach wave. So it's written here. It will turn into only a Mach wave. And if you remember, we discussed what a Mach wave is. It is a disturbance to the flow, but just generating infinitesimal changes. And in reality, Mach waves are isentropic waves. If you don't remember it, please revise our class videos regarding that. So this occurs when we are very far away. Of course, the detached shock wave sits in front of the body, very strong. To summarize, very strong, right in front of the body, almost like a normal shock wave, gets weaker and weaker and weaker as you move along, and at very far away from the body, it basically turns into a very weak Mach wave. Okay, so this, as you might understand now, this is not a very simple process, meaning that if we end up very simple process, meaning, for example, if we are interested in calculating variables after or downstream of this detached bow shock wave, we are interested in the pressure level, temperature, stagnation pressure, density levels. After this, we need to do a zone by zone calculation because of the curved bow shock wave. The geometry of the shock wave is curved, plus its weakness is a function of location, okay? Or its strength, it's not weakness, but its strength is a function of location. That is also changing. So therefore, that kind of variation, the geometry is curved plus the strength of the shock is changing with location, of course, creates variations in pressure, temperature, stagnation pressure, and density, you know, at different points just behind the shock wave. We cannot, for example, do what we did in the sample problem that we solved in the first hour. We said it was not a detached shock wave case, it was an attached oblique shock wave case. We said whatever pressure that we are having here, it will be equal to the pressure on the surface. That was the case in the sample problem. In this case, where we have detached bow shock, we cannot do that because there will be a pressure gradient, let's say, along this direction. The pressure will change. So everywhere on each point here, there will be a different static pressure. And on each point here, there will be a different stagnation pressure and different temperature and different density. So that, of course, needs to be calculated. I mean, theoretically, you can do that. It is possible you can divide, if you know the shock geometry, by the way. Calculating the shock geometry, it's not very straightforward. either, for example, let's say you do a wind tunnel experiment, visualize this, obtain the shock shape, and then divide the shock wave into small segments, and then do these calculations one by one and try to estimate. So this is one thing, one possible way that you can do. And this was mostly done before the advent of computers in the, 1950s and 60s. Actually, they were the glory days of supersonic flight when everybody was without computers. Actually, they were trying, they came up with all kinds of supersonic flying machines. I mean, people went to the moon for that sake. But in any case, these days we do heavy computational fluid dynamics analysis to get both the shock wave geometry and the conditions after the shock wave. In addition, we do still experiments just to verify the shock wave shape is correct and consistent with what we get from numerical simulations. Okay, we do wind tunnel tests. When you do wind tunnel tests, it's quite difficult, if not impossible, to measure all these quantities after the shock wave. We really need to be careful, because as soon as you insert some kind of probe, for example, to measure pressure, it will induce its own, potentially it could induce its own shockwave field. So you really need to be careful what you're measuring, but you could measure, at least if you put some holes on the surface, you could at least measure the surface pressures. That can be done quite easily. Anyway, so these are some, let's say, extra information regarding how we need to, regarding some practical engineering issues in aerospace engineering, regarding how we need to deal with different physical aspects of shock waves in general. Okay? Any questions up to this point?
Hocam,
Mhm.
in the microscopic level, can we say that every oblique shock has a detached bow shock part due to the smoothness on the edge?
Well, if you take a microscope and really zoom in, you could see that, I guess. You could see that, because it depends on the surface geometry. And if you really zoom in, for example, to this surface, I don't know, it looks very smooth here. In reality, if you really zoom in, look it under a microscope, it will probably look something like that, right? In the microscopic level. So the shock wave, there could be a very locally detached shock wave here, but right now we are not concerned about this.
Thanks, sir.
Hocam, can I ask something?
Sure.
About 2 slides ago, but in a duct, no, not this one, before that, I guess. Yeah, in that part, we said there was a incidence shock and reflection shock, and they coincide with each other at point B.
This one.
Yes. Is this always the case, or we are looking at something specific here?
No, there will always be a reflected shock wave.
No, I mean, will they coincide at a point like on the upper surface?
I mean, it's not coinciding, it's just getting reflected. The shock wave, physically, when it hits the wall, it gets reflected like a light ray. It gets reflected. Only thing is, if this was a electromagnetic wave, like a light wave, it would reflect symmetrically, yes, if this was a mirror, for example. But in this case, it does not do that. It does not reflect with the same beta-1 angle. The reflection happens such that the reflected shock wave sits at a different angle, phi, which depends on this inlet Mach number M2 here. Okay?
Okay, hocam, I understand. Thank you.
Any other questions? Okay. We already talked about this, and we already talked about this. Good. So let me stop this. And I will go back to the whiteboard again. Okay, good. So we covered quite a bit of shock waves in general. To summarize, we started from normal shock waves, learned how to calculate properties behind normal shock waves, and then we discussed the case of oblique shock waves, and we did lots of discussion. Now, in addition to normal shock waves and oblique shock waves, a third type of physical phenomena happens that we need to consider in, let's say, supersonic flow fields. Now, these are called expansion waves. So now that's going to be our next topic. And in fact, we do have a special name for them. We call them Prandtl-Meyer expansion waves. Okay. Now, we say expansion waves. What do I mean by that? We mean that the flow actually gets expanded, which meaning that it's not getting compressed. So if you remember, I guess, explained it some while ago. Let's say in the case of a ramp, okay, we do have, let's say we have some shock wave here. We do have a streamline and then suddenly turning like this way. So for the external flow case, let's say it's happening like that, and let's say we have a streamline that is very far away, really far away from the surface, so it's not actually disturbed because probably it's going through a weak Mach wave. So it's just going straight. Now, when we consider this area change between the wall and this very far streamline away from the surface, you see that, for example, if you compare the area here to the area here, it basically shows a reduction in area. So what happens in reality, especially for an incoming supersonic stream, is that the gas, because gas gets very much compressed when the surface moves towards the gas like that. And that compression is due to this sudden area decrease due to the change in geometry. It's like you're pushing the gas towards this streamline, and this streamline is so far away, it's not actually getting disturbed. So basically you are trying, it's like a piston moving towards the gas. So it's like you're compressing the gas suddenly. So that's why that's one of the reasons, the static pressures are increasing and everything for a compressible gas. Now, when the opposite happens, meaning instead of pushing this wall towards the gas, if you pull it away from the gas, so let's say your ramp is moving on the opposite side, like that. In this case, the gas experiences a sudden increase in area. Okay, sudden increase in area. And for a supersonic stream, this sudden area increase physically corresponds to not a compression, but expansion of the gas. Okay, sudden expansion. So now if this happens, if the geometry suddenly moves, as it's written in your book, away from the gas, like that, okay, again, the incoming supersonic stream, M1, must adjust itself to the geometry again, M2, but the physical process is different. The physical process is not compression anymore, it's expansion, and therefore we cannot have shock waves, but this sudden adjustment of direction occurs through what we call an expansion wave, which is basically, if this is kind of the boundary corner, which is basically a set of many Mach waves sitting one after another slowly, and each one infinitesimally turns, and one just a little bit, let's say an infinitesimal angle, each one turning it a little bit and a little bit more and a little bit more and a little bit more, and at the end of the expansion wave region, the flow vector is now turned and parallel to this wall, this at this stage. This is called the phenomena happening here, the physical phenomena, is called an expansion fan, or expansion waves, let's call them expansion waves. And or sometimes it's called an expansion fan. Expansion fan, it's like yani yelpaze gibi gözüküyor, onun için expansion fan. Or sometimes we call it Prandtl-Meyer expansion fan. This region that is filled with many number of Mach waves, basically, or expansion waves. So Mach number is greater than 1, it is supersonic, and then it has other conditions. And also we are interested in obtaining the conditions after the expansion fan. Generally, the fan starts with what we call the front boundary. This one is called the forward Mach line. Forward Mach line, and ends with another, the last wave, let's say, and this is called the rearward Mach line. Okay. And according to our analysis definition, the forward Mach line sits based according to this, I mean, with regard to this incoming surface, sits at an angle mu1. So this is mu1, the forward Mach wave angle. The backward or the rearward Mach angle sits at an angle from this surface at mu2. Okay, so therefore this expansion fan is bounded upstream by this Mach wave, that is sitting at mu1 angle. So this mu1 angle can be calculated if you remember our discussion of how Mach wave angles are related to Mach numbers. This mu1 angle is related to arc sine 1 over m1. Okay, a few classes ago we discussed how these Mach wave angles are related to the Mach number, and similarly mu2 is related to the Mach number after the expansion fan. The last one, or the rearward Mach line, is related to Mach 2. So these lines, I mean, these the waves that are constrained between the forward and the rearward Mach waves, there are many of them, and as I told you, these are not shock waves. Each and individual one creates an infinitesimal change in flow direction and flow properties, and therefore each one is actually a Mach wave. And as if you remember from our Mach wave discussions, yes, their angles are calculated like this, but if you remember also, each Mach wave, in general, a Mach wave is an isentropic process. So let's say the infinitesimal entropy generation across each one of these waves in the fan is actually 0. So across across each Mach wave. Mach waves are isentropic processes. So in reality, when the flow is expanding through a corner like this, a supersonic compressible gas is expanding through this corner or corner like that, then what happens is it has to go through this expansion fan, and since this expansion fan basically does not generate any entropy, it's an isentropic process. Okay, so it's expansion across an expansion fan. I mean, the physical process of expansion through this expansion through the expansion fan is an isentropic process. So this is totally different than what we learned for the shock wave related issues. You know that shock waves are not isentropic processes. And therefore we do all, we discussed a lot about this. An expansion fan, on the other hand, indeed is an isentropic process. And so therefore it actually greatly simplifies our lives and equations. We will see now, and our objective is again to calculate the properties after the expansion fan, given the properties before the expansion fan, and given, for example, this geometrical change. So if this is some kind of theta angle, kind of a reverse ramp angle, if you might want to say, given that geometrical change, given inlet conditions, what kind of flow parameters, pressure, density, temperature, and Mach number will I have after the flow or streamlines go through this expansion fan. Good. So that's the next thing that we're going to learn. We will also derive or obtain relations according that we can apply to the physical process of expansion fans that we observe in supersonic flows. Okay. All right. So let's stop here. If you don't have any questions, we will continue tomorrow with the subject of Prandtl-Meyer expansion waves or expansion fan at 1:40 tomorrow. Any questions at this point? No questions. Okay, everyone. 14 of you out of 70 students taking this class in my section. I will see you tomorrow. I will talk to you tomorrow then. Okay?
İyi günler hocam. Görün kendinize.
İyi günler hocam.
İyi günler, teşekkürler.
Hocam.